So I think let's start. So we're going to continue talking about this algorithm, approximate policy iteration. And then we're going to talk about another important result, which is called a performance difference lemma. Right? You will see that this is actually very similar to the simulation lemma that we talked about. And the proof is almost identical as well. All right, so let's just do a quick recap. So Tuesday we talked about, we spent actually a lot of time talking about supervised learning. Hopefully that reminds you something about what you learned in the intro to machine learning class, right? And then we said that our hope was that if we could solve reinforcement learning via reduction to supervised learning, then it would be nice, right? Any advancement that we could have made on supervised learning will immediately be translated to advancement in RL. But because we're dealing with RL, we don't have data set. So we spend a lot of time talking about a process where we can draw state action pairs and also get unbiased estimate of some policies Q values. All right, so the key message for supervised learning part is that it often just works, right, in both theory and in practice, if there is no training and test distribution mismatch. Right, so if there's a mismatch, then it's become really hard for us to say anything about the performance of the supervised learning algorithm, right? Unless you introduce additional assumptions, which is, there's a field called transfer learning, but there people have to introduce different assumptions, right, to make that work. Right, and then we talked about this data generation process, and we defined two procedures, right? The first one is called rolling in, which is you're starting from the first time step h equal to 0, and you're just executing the policy up to a time step h, which is pre-sampled with probability proportional to gamma to the power of h. Right, so here what we did is that we sample a time step h with probability proportional to gamma to the power of h. Right, and then we just roll in the policy all the way to this time step. And then the rollout step is used to get an unbiased estimate of Q pi at particular state SA, right? So here, I'm trying to get an unbiased estimate of Q pi SH AH. Right, so what I can do is I just roll out my policy pi. And every time step, I'm going to do a check. Right, so with probability 1 minus gamma, I'm going to terminate this process. So imagine that you are here, you flip a coin, and that coin tells you that you need to terminate. Right, so if that happens, we just terminate and return the straight sum of the rewards in this red segment. Right, so this is the process that you get a triple where state action pair is sampled from this distribution, and the scalar y is an unbiased estimate of the Q pi at state action pair SA. Right, so any questions for this data generation process?
So are you still executing policy pi on that red segment?
Yeah, because I want to estimate Q pi, right? The value of Q pi.
So then in this process, when we are generating data at each step and then training and then approximating Q, after we get the Q, we update our policy, right?
Yeah.
And then do we use the new policy to again do this roll in, roll out?
Yep.
But then doesn't that bias against, or like, doesn't that favor, like we're getting the data based on our policy, right? So if we start down this certain path of improving the policy based on the data that we sample, isn't that kind of like a self loop where we're getting the data and then training on something similar?
Yeah, we will get there today.
Okay.
Yeah, maybe keep that question, for a few more minutes. Right, and then next week we will talk about fix for this problem. All right, so let's just move on. So let's just quickly recap okay, we actually haven't talked about the algorithm yet. So let's just introduce the algorithm first, and then quickly wrap up the algorithm by talking about the pros and cons for this algorithm, right? And yeah, so that corresponds to bullet point 2. When does this algorithm actually work, right? By work, we mean, can we guarantee monotonic improvement? Because if you recall, right, policy iteration guarantees you monotonic improvement if the transition and reward function are known, right? And then the last piece of this lecture is this importance result called performance difference lemma, right? So this is very similar to the simulation lemma, you will see. All right, so we talked about how to get the data set, right? We prepared everything at this moment for performing a supervised learning problem, right? Especially a regression problem. So we have a data set. Let me just remind you. So we repeat this loading in and roll out process for n times for a fixed policy, right? So this is given a policy pi. We repeat this process n times. So we get a data set that consists of state action and a scalar y triples, right? So here, Si, Ai is from d pi, and yi is an unbiased estimate of the target that we're trying to approximate. Okay, so now we want to estimate a q pi. Let's just do least square regression, right? Let's just try to find a function q from our predefined function class. Maybe your function class q could contain all possible 10 depths decision tree, right? So let's try to find the best decision tree with depths at most 10 that can fit my training data. Right. And then again, let's not worry about the optimization procedure here. Like for decision tree, we have algorithm to fit that, right? For SVM, we also have algorithm to do that because it's a convex optimization problem. And for general neural network, we could do gradient descent. And we're going to talk about gradient descent, stochastic gradient descent in the next few lectures. All right. And let's just assume that supervised learning succeeds in the sense that the estimator Q hat is pretty accurate if we test it under the same distribution that we use to generate the data. All right, so this is a distribution that we use to generate data. Sorry, it's mu0. Right, remember SIAI is from d pi mu0. Right, so I'm not doing any distribution mismatch. I'm just training a function q hat under data set generated from this distribution d pi sub mu0, and I'm evaluating under the same distribution. Right, and again, this delta thing usually shrinks in the order of 1 over square root of n, and sometimes it could be even faster. It depends on what parameterization you use for the function class.
Can I ask a clarifying question? What's going on with the argmin? Like, what's the class of like curly q that we're minning over?
Yeah, so let's do an example, right?
Okay.
So let's do, for instance, linear regression. All right, so let me just define.
Okay, oh, so I see. That's just a class of estimators for the q function.
Yeah.
Oh, I see. Okay.
But nevertheless, let's just do a quick example.
Yeah, right? Sounds good.
It could be useful in the future as well. So imagine that I have a feature vector phi that takes SA as input and outputs a vector in RD. So this is like a feature representation of my state and action, right? Maybe this encodes the position of the state and the index of the action, right? Something like that, right? Like in LQR, this phi SA could be the concatenation of the state and action, right? Because the state and action, they both from Euclidean space, right? And my Q, this, I don't know how to write this mask code Q. It is all possible linear functions with respect to that feature vector, where theta might be from a ball with radius 1, for instance. Right? So these are all the potential, candidates of my function, right? But I don't know which one it is. So let's just do least square linear regression, right? Right, so that's the usual linear regression problem. All right, any question for this regression oracle? So here we are doing abstract. We are basically reasoning this regression in a more abstract level, right? So we are given a function class. Maybe you still remember this is called hypothesis space, right? If you still remember the VC theory stuff. So we give a hypothesis class, and we're trying to pick the best hypothesis that fits the training data. Okay, so let's just put things together, right? So this is an iterative algorithm. So let's just start from some initialization. So I'm just going to pick a function in the function class, right? So think about the linear regression as an example. I'm just randomly initialize my theta vector, right? And then I just act greedily with respect to my estimator. So this is like the first step, right? Okay, so now let's imagine that inside iteration t, right? I have a policy pi t that is available from the end of the last iteration. Let's just feed it to this data generation process, right? Remember this rolling in and roll out process. Let's just repeat it for n times. And now we get a data set. Right? So the data set is basically you have state action pair sampled from the column policies, state action distribution. And your regression target, yi, is an unbiased estimate. Sorry about that. Is an unbiased estimate of the thing that you're trying to estimate. Right? So now with this data set, let's just feed it to the least square regression oracle. Right? Imagine, this is a linear regression oracle, for instance, or it's a regression decision tree oracle, for instance, right? All right, so then we get an estimator, Q hat T, right, which is the best hypothesis, the best candidate that fits the training data, right? Minimize the loss, the training loss. All right, so our hope is that, somehow maybe this QT approximates Q pi T. Right? After all, we are doing regression, to predict Q pi T, right? Hopefully, it predicts well. And if that is the case, let's just do a policy improvement step, right? Which is the step that you would do in policy iteration if you had the ground truth Q pi T. But here, we are replacing the ground truth by our estimator, right? Because we don't know the ground truth Q pi T. Right? And let's just close the loop. That's the algorithm. Right? So if you would like to see a more standard pseudocode, this is, the slightly more standard pseudocode, right? You have initialization and you start writing a for loop, right? Starting from, iteration 0 all the way to some point when you pretty confident that this is converged, for instance. All right, so the first thing you always do is prepare a data set. And this is just repeating this process, loading in and roll out process for the column policy n times, you get a data set. Right, and then you do least square minimization. And then you just pretend this estimator, Q hat, as a pretty accurate estimation of the ground truth Q pi T, and then you just do it a step of policy improvement. right? So that's basically the algorithm, right? So, contrasting this against the policy iteration algorithm, right? So here we are using data-driven approach. We're using regression oracle to estimate our policy's Q value. So this step is approximating. Right, because now we are operating in the setting where we don't know the transition matrix P, we don't know the reward function R, right? So we cannot compute this Q pi T in closed form solution. So we have to use data-driven approach to learn that. And a particular way that we talked about today is use regression oracle.
Professor, can I ask a quick question?
Mm-hmm.
So suppose the problem you're learning is like a self-driving car, and then after you sample some data, now you update your policy. So do you want the car to return to the origin, or do you want the car to continue where the row in row out process has stopped in the previous iteration of the sample generating process?
Yeah. So in this setting, we assume that you reset from the initial state distribution.
Okay.
Right. So this process, so rolling always happens from U0, right? Start from U0. It's like you always reset your car. Every morning, your car starts from your garage, right? Or your parking lot.
Okay. Thank you.
Right. So, okay, so now let's see, when does this algorithm actually work? Oops, okay, I'm showing too much stuff. Okay, ignoring the picture for now. So let's just recall the policy iteration algorithm, right? So in the policy iteration setting algorithm, if we know the Markov decision process, in the sense that this matrix P and this reward function R are known, right? So we can actually guarantee that the policy iteration is making monotonic improvement, right? It's like a gradient descent, a gradient ascent, right? It's doing hill climbing, it's getting policies better and better until it hits the optimal, right? So that's great. This is kind of the phenomenon that we want, right, in both theory and in practice. So you may hope this approximate policy iteration algorithm actually gives you monotonic improvement, but the fact is that it can't, right? So here, let's just, instead of proving that, let's just look into this example, right? Trying to sort of get a sense of why it does not guarantee monotonic improvement. Right, so here I'm just plotting some example. So x-axis, think about this as the space of state action pair. Right, every dot in this x-axis is a pair of state action sample. And the y-axis is the value of Q pi. Right, so let's see at iteration t, I have policy pi t, and this green curve is the underlying ground truth Q pi t. Right, so the green curve is telling you the ground truth Q pi t, but of course you don't know that, right? So what we did is that we generate a bunch of data. These are the green dots. So these are the SA pair from d pi t mu0. And we generate a bunch of data, these green dots from d pi t, and we do regression. And for instance, this is the function that we found, for instance. Right, so here, the key point is that I'm actually doing really well in this region, right? Because I see a lot of training data in this region. And in this region, I can guarantee that my estimator is pretty accurate, right? But another key message here is that under this region, I really lost out control of my prediction because I don't see any training data except like this 1 or 2 points, right? So this is beyond my control. And this region is good because I have a lot of training data, right? So maybe my estimator will look like that. where I'm pretty accurate here, but here I'm just crazily overestimating the value. Right, so that could happen. I mean, we cannot sort of control it to not happen, right? So this could happen. All right, so now if I be greedy with respect to my estimator, remember my pi t plus 1 is argmax of a q hat t, right? It is very likely that my policy will start visiting state action pairs that have high value in my estimator, right? Because that's what my estimator tells me, like, hey, there are a lot of values and you should actually go there. So maybe we will find a new policy pi t plus 1 such that it visits a lot of these states, right? The states where the previous estimator has high value. Remember, pi t plus 1 is argmax q hat t. All right, so let's see, this red curve is the ground truth value for q pi t plus 1. Right, so now I repeat this regression process. Again, I get a bunch of red dots from d pi t plus 1 mu 0. These red dots is from right, and then I do regression. And let's see, this dashed line, red line, is the function approximator that I got. Again, there's two key messages, right? The first message is that I actually did really well under a region where I have a tons of training data, right? So this I can guarantee because, if I see a lot of training data in this region, my estimation should be accurate. But again, here I cannot avoid it, giving me this kind of weird case, right? In the sense that it's crazily overestimating the ground truth because I don't have any data, right? It could either be underestimating or it could be overestimating. You can't really control what's going on, right? So if that's the case, remember my policy update, my new policy update now will be argmax for a of q t plus 1, right? So in other words, the new policy might just go back to the previous region, right? Because this estimator is telling us that you're completely overestimating on the space where you previously had these green dots. Right, so in other words, you may find a policy that actually switch back to the previous policy, right? So you're generating a new policy that visits these red dots again. And if you repeat, then you may generate another policy that visits the red dot, and then you repeat, then a new policy visits the green dot. So you can actually get this oscillation behavior. So you cannot really prove that the new policy will actually do better than the previous policy. Right, so this actually would happen. And you can actually come up with a Markov decision process to show that that happened. But we're not really gonna go into the details of that. So the issue is really the distribution mismatch, right? So we have training data. So this green dots are the training data, right? But when we execute the policy is actually visiting different state action pairs than the training data. Right, so this is not supervised learning in the sense that you train on the test examples and you're testing on a you're training on the training examples and you're testing on examples that look very similar to the training examples. Right, so yeah, so the key issue is we are making very sudden change in the two policies, right? So pi t plus 1 and pi t, they could be widely different in the sense that these two distributions could be widely different. Right? And our estimated q hat t is only good under the training data distribution, which is the distribution induced by the policy pi t. Right? But when we evaluate it under the new policy's state action distribution, then we cannot guarantee anything. Right, so remember, this is trained under SA from d pi mu 0, right? So that could be very bad. And one of the fix is you really need to have a very diverse initial state distribution. All right, so this says that, so this condition says that maybe for all policy pi, right, for all state S, d pi mu 0 S over mu 0 S is bounded by some constant that is less than infinite. So in other words, this is saying like, maybe my initial distribution mu 0 is pretty wide, all these regions that will be visited by different policies, they're sort of covered by my initial state distribution. Right, so there's a question.
Could another method, like, so the issue is also that like the sampling is following that specific policy, and that's why you end up clustering those state action pairs in the distribution, and that keeps switching. Could one solution also be to add some noise when you're sampling? So like while you're sampling, just randomly, instead of following the policy, just sample some other state action pair. Like that would also introduce the diversity, right?
Yeah, you're right. Yeah. You can do that for sure. Yeah. Right. So let's just focus on this initial state distribution for now. Right. So if that term is diverse enough, then we are pretty good, right? In other words, in the sense that our estimator Q hat T can approximate Q pi T almost everywhere. Right? Because remember, our data set is generated from d pi mu 0, right? And d pi mu 0 is written as 1 minus gamma times mu 0 plus 1 minus gamma times gamma of p pi 1, so on and so forth, right? So if my mu 0 is diverse enough, then this pretty much says that my training distribution is diverse enough too, right? Because my training distribution always contains this component of the initial distribution by definition. Right, so basically this says that we need to be diverse. Like we need our data generation distribution to be diverse enough. Right, diverse enough such that it will cover all the possible traces from all the possible policies that you would encounter in the future. Right, so this corresponds to, for instance, autonomous driving. This is like, let's just, in order to make autonomous driving to work on Ithaca, let's just ask tons of human drivers and drive all these cars around. Right, hopefully it covers every inch of Ithaca under all kinds of weather condition and so on and so forth. Right, whether or not this is scalable, I mean, unclear, right? A lot of companies are actually trying to do that. Like you can imagine, like Tesla probably is collecting tons of samples everywhere, right? And when I was at Pittsburgh, these companies like Uber self-driving, so Uber had a self-driving unit at Pittsburgh. So we could often see like Uber driving these self-driving cars were driving around, right? Right, so that's the end of this second bullet point. So in the next few lectures, we will talk about a way to fix this, right? So we see that the issue is the distribution mismatch. So you train a policy from the previous distribution, and now your new policy is actually inducing a distribution that is widely different from the previous distribution, which was your training distribution, right? So if we have a way to sort of regularize this change in distributions, in other words, if you can make very incremental update, then you will see that this problem will actually go away. Right, so this is like gradient descent, right? We don't want to make a very sudden change on our solution. We just want to follow the gradient direction a little bit. And that guarantees us, gradient descent is making monotonic improvement. So this is what we hope in in RL as well. So in the next few lectures, we will talk about gradient ascent methods for reinforcement learning. All right, so any questions so far? So this approximate policy iteration algorithm is really sort of a motivated example for the incremental algorithm that we're going to talk about in the next few lectures, right? So policy gradient methods and natural policy gradient methods and conservative policy iteration. So these are the three algorithms that we're going to talk about. Right? And they all share the same philosophy. Let's make very small incremental update on our policies, right? So that the new policy state action distribution is not different from the previous policy state action distribution by that much. Right? It's like gradient descent, you only move along the gradient direction a little bit, right? If you are moving, if the distance that you move is infinitesimally small, then we can guarantee that we are doing better than the previous solution. Right? So that's the same philosophy that we're going to use in RL. Right? So if there's no question, then let's switch topic and let's talk about performance difference. Right? So that's a key result that we're going to use for showing policy improvement in policy gradient methods. All right, so let's talk about the motivation for this thing. All right, so let's recall simulation lemma. So what's the question that simulation lemma was concerned about? Right, so simulation lemma says that I want to sort of quantify the difference between a single policy's performance under two different Markov decision process. Right, so if I give you two Markov decision process, P hat P, let's assume that reward is shared, right? And then a policy pi, I want to understand the difference between the values, two values, right? So this is the expected total reward under pi and p hat, right? And the second term is similar, the expected total reward under pi and under transition p, right? I want to sort of quantify the difference between these two performances. And I want to quantify the difference between these two performances, use the difference between the two transitions, right? Because these two processes, they share everything except the transition operator. Right, so simulation lemma tells us that we can actually bound the performance difference between these two models by using the model one-step disagreement measured under the L1 law. Right, so the performance difference lemma that we're going to talk about today has a very similar flavor. But now instead of focusing on two Markov decision process, let's just focus on one Markov decision process. Right, so I'm only going to concern one Markov decision process. But what's changed is that now I'm interested in quantify the values of two different policies, pi and pi prime. Right? I'm interested in the performance difference of this policy pi, these two policies pi and pi prime under the same Markov decision process. Right? So this is really, sort of the motivation for policy improvement in the next few lectures, right? Because I get a policy pi, I somehow make an update, I get a policy pi prime. So I want to quantify, the difference between these two values, right? Hopefully that value is increased. So that's great. And that's why, we want to understand the difference between these two values, right? And our hope is that we can actually quantify the difference by the difference between two policies, right? So one extreme case is that if pi and pi prime are extremely close to each other, then our hope is that, these two values, the performance difference between these two policies, they should approach to 0 too, right? So in other words, we might want to quantify this value by the difference between pi and pi prime. right? So that's a question that we want to answer by using this performance difference lemma. Right. So yeah. So in other words, we trying to sort of compute or get a relationship between the difference in performance and the difference in policies. All right. Any questions for the setup? Right. So you really should think about this two policies as some two policies that you computed by some policy improvement algorithm, right? So you have policy pi at this iteration, somehow next iteration you get a new policy pi prime, and you're trying to ask yourself, if the value of pi prime is actually bigger than the value of my previous policy pi, right? So this performance difference lemma will tell you the difference. Okay, so let's just set up the notations. So these are the usual stuff. So infinite, discounted infinite horizon Markov decision process, state visitation, state distribution, which is the exponential mixture of all this state action distribution over different time steps, right? The usual stuff. Okay, so I want to introduce a new definition, and I think this is pretty much the last definition that we're going to introduce for this course. Okay, it's not really a new definition, it's just sort of a rewriting for this difference between q pi and v pi. So in the literature, we call it advantage function, and it's often written as a subscript superscript pi SA. All right, so this is called advantage because we're sort of trying to quantify the advantage of deviating from pi for one step. All right, let's draw a picture. So at state S, so one strategy is follow pi all the way to the end, so we get value v pi s, right? So this A is from pi s. Okay, so now we are interested in about the advantage of a different process, a process that actually deviate from pi for one step and then keep following pi. So in other words, I'm trying to see if I can actually get something better by, instead of lessening to pi, let's just try out some other action. Right? And then I'm just going to follow pi all the way to the end. Right, so I deviated from policy pi for one and only one step, and I'm interested in to see if this deviation gives me something better, right? So I think that's why in the literature people call it advantage function, and the difference between these two values is defined as the advantage function. Right, so this is like the advantage of taking A and then follow pi over the process of following pi all the way to the end. Okay, so let's just do a quick sanity check, right? So the advantage over itself is actually 0, right? Because A pi s, this is just like q pi s minus v pi s, right? So you're not deviating from pi, right, at all, because you just follow pi at s and then you keep following pi, right? So your advantage over yourself is actually 0. Right, so this is actually nice because now we can actually rewrite, it's a completely equivalent rewriting. So we can rewrite the policy improvement step in policy iteration by using an advantage function rather than the Q function. Right? You should convince yourself that the argmax on the left-hand side and the argmax on the right-hand side, they're equivalent. Right, so this is that the policy improvement step actually is trying to seek an action that has the largest advantage over the current policy pi. So that totally makes sense, right? So you're trying, so you as stated here, and this is v pi, and let's see, you have like 3 actions available at state S, and you're just trying to pick an action that has the largest advantage over the current policy pi. Right, and again, this step is a completely like equivalent rewriting, right? Because advantage is the difference between q pi and v pi, and v pi is action independent. Right, so any questions about this new definition and hopefully the last new definition in the semester? Okay, great. Yeah, so here I'm just rewriting the definition of the value function, right? So recall that this is the expected total discounted reward. All right, let me just present the performance difference lemma, and then in the next slide, let's just break them down term by term and do a quick explanation, and then we jump into the proof. All right, so if you look at the left-hand side, so this is the quantity that we care, right? So the difference between the performance of the 2 policies. And on the right-hand side, this is sort of saying that the difference, the performance difference between 2 policies is the averaged advantage values. All right, so let's see if I can draw this. So we have S0 here, and let's see, we get a trajectory from following policy pi. And along these waypoints, right, I'm computing the advantage of pi prime over SA. Right, and then I'm averaging over this advantage. Advantage here, advantage here. Then I average over this advantage. And again, here, there's no inequality involved. Everything is equality. Okay, so let's move on to see, let's draw some pictures again here, right? I'm trying to get a better understanding of what's going on. Right, there's a left-hand side is again, these 2 non-overlapping, potentially non-overlapping trajectories following policy pi. Right, and we care about the difference between these 2 potentially completely non-overlapping trajectories, right? So, and we have argued it many times, directly quantifying the difference between 2 completely non-overlapped trajectories is very hard. And the common trick that we have seen many times at this moment is that let's introduce some middle ground, right? So maybe let me just follow pi for 1 step, 1 and only 1 step, and let me just switch to pi prime afterwards. So this is my new middle ground. So this, so let me call it 1, 2, 3. Right, so we cared about difference between 1 minus 3, and now we can just rewrite as usual. Right, so again, I'm claiming that for 1 minus 2, you're just looking at the difference between these 2 segments. Right, so at this stage, you should convince yourself that here, potentially you can do some recursion step, right? Because the difference between these two segments is basically the same situation that you faced at the first stem step, right? It's just, you just move the one step ahead, that's it, right? But the situation you face is the same, like the difference between two non-overlapping trajectories. Right? So this step, hopefully we can convince ourselves that recursion can work out. So what about 2 minus 3? Right? So if you recall the advantage definition, 2 minus 3 is exactly the advantage function definition. Right? So let me rewrite advantage. A pi prime S0 A0, let's call this A0, is actually Q pi prime S0 A0 minus V pi prime S0. All right, so this is exactly equals to 2 minus 3, right? Because what is this trajectory? This trajectory says that I first follow A0 and then I follow pi prime, right? And this trajectory says that I just follow pi prime all the way to the end. So the difference between these two segments is exactly the definition of advantage, right? What's the advantage of deviating from pi prime at the very first time step and then following pi prime? Right? What's the advantage of this one step local deviation? So this is exactly what this term 2 minus 3, right? I deviated, instead of lessening to pi prime, let me just deviate for one step, see what happens. Right? So if you put these pieces together and convince yourself that recursion works out, then the proof is done, right? Because 2 minus 3 is the advantage, and we have an advantage term in the final expression. Right? All we needed to do is get advantage for every time step and then average time back. Right? Any questions so far?
So d pi, that's a state action distribution, right? But here we're only, like in this lemma, we're only sampling S from d pi, but we're getting A from all possible actions from state S.
No, so A is from pi 2, right?
Yeah. So we're not looking at the action given by d pi, right? Like, because that gives a state action pair, right?
Oh, I mean, they should be. You should think of, they're the same, right? Because for, yeah, okay. So what is d pi S? So remember, we just defined the state distribution for this moment, right? I mean, I can just easily write this as this. This you should convince yourself is like times pi AS.
Oh, okay, I see.
Right? Because my action, like how you get this action, right? The action is always sampled from pi, right? So just use the Markov property, right? Because the action is always generated by looking at the current state and then sampling an action from the policy, right? So this is this expression is talking about, right? Yeah, so you're right. So in other words, I can rewrite this as expectation of SA from d pi S0, the advantage of pi prime SA. All right, so we can just quickly put these pieces together to arrive this very simple proof, right? So we just write out the difference, and what we did is introduce this middle ground, right? So we do, this is 1, this is 2, 2, 3, right? So this is exactly the middle ground that we're talking about. All right, so now let's take a look at 1 minus 2, 2, 1 minus 2. Right, so what I can do is rewrite this, use the Bellman equation, right? So this is equal to, so here, one thing to notice is that I'm using stochastic policy again, right? So, but everything works for deterministic policy. But you should think about deterministic policy as a special case of stochastic policy, right? So this is expectation of A0 from pi S0 So this is just Bellman equation. I'm just rewriting v pi using Bellman equation. And now I can cancel these two rewards, right? Because they are under the same expectation and they're the same reward. Right? And then I can pull this gamma and expectation out. Right? Because they are the same gamma, same expectation. And if you do this operation, this is the simplified equation you would get. Right? Remember, reward got canceled out, expectation is pulled out. So now you get to a situation where you can actually apply recursion here, right? This is sort of the situation that you actually faced from the very beginning. Right? And the second term is just the advantage. Right? Nothing fancy here, it's just the advantage, right? Because let me just remove that. Because this term is nothing but just q pi prime S0 A0, right? So I take action A0 and then I follow pi prime. So that's exactly what this quantity is telling me. And what about this one? I can just rewrite this as expectation of A0 from pi S0 of b pi prime S0. Right? So this is equivalent because my value function is independent of action. So I can just add some expectation with respect to action in front of it. It does not going to affect anything. Right? It's like expectation of y of fx is nothing but just equal to fx, right? Because my function fx is independent of y. All right, so then if we just put these two pieces together, this is the equation that we get to, right? And this is nothing but the advantage prime 0 E0. Right, so again, this quantity is concerning the advantage of deviating from pi prime for one step. Right, so if you put everything together, then if you apply recursion here for infinite many time steps, you will basically get to the final expression of this lemma. Right, so this is exactly the same proof that we had for simulation lemma. Right, so in summary, so we just proved this expression, right? So this the usual proof strategy, right? And now if you use the fact that this Q value is always bounded from 0 and 1/1 minus gamma, right? And we add absolute values on both sides of this expression, and we arrive to this sort of simplified expression, right? So this is way more simplified, in the sense that we can bound the performance difference, the absolute value of the performance difference between two policies by using the disagreement between these two policies, right? Averaged over one policy's state distribution. Right? But again, you get a quadratic blow up on this 1/1 minus gamma. So picture-wise, this will be very similar to the one that we draw for simulation lemma, right? So if we had the S0, I follow policy pi, then along these waypoints, right? So along these waypoints, I will just check, what pi prime would say instead of pi, right? So what pi prime would say, and right? And I care about the deviation, the disagreement between pi prime and pi. So maybe this delta, right? And then I average this delta together. This is the right-hand side of this inequality. Right? Again, we converted the difference between two potentially non-overlapping trajectories into this one-step disagreement between policies. Right, so this is kind of nice because we don't really know how to sort of deal with two non-completely non-overlapping trajectories, right? But this one-step deviation is kind of nice. We don't have to worry about infinite disagreement. We just needed to care about the difference between two policies at the current moment, at the current state. Right, so this allows us to reason, the difference between two infinite long trajectories by this one-step difference. Right, let's just do a quick sanity check, right? So if pi prime and pi are exactly the same, then this basically tells us that the performance difference between these two policies is 0, right?
So just a clarification question, but the output of policies is so these pi of like dot given s, that's the 0, that delta distribution, right?
Sorry, say it again.
The pi that you have in that difference over there, like pi of the dot given s, that's the delta distribution, right? It's 0 or 1.
Oh, you mean this one?
Yeah.
Not necessarily, right? Not necessarily if my policy is stochastic.
Okay, yeah.
So if your policy is deterministic, yes, I mean, this distribution will be delta distribution, right?
Yeah.
Right.
Okay.
But this whole proof applies to any stochastic policy, right? So stochastic policy will be useful when we get into the policy gradient region, right? There we will concern stochastic policy.
Sorry, so I'm just a bit confused about the term inside the expected value. Like, I don't quite understand what that's saying. Like, is it the difference in probabilities? Like, because like isn't the result of pi like an action? And I don't really get. You're not.
Yeah, so that's basically the same question, right? So if your policy is deterministic, right, I can always express a deterministic policy by a stochastic policy, right? By creating a delta distribution.
I'm confused as to what the term inside the expected value means.
You mean this term?
Yeah.
This term, right?
Yeah.
So that's okay. So let's first think about the simplified setting where both policies are deterministic policy. All right. So in that case, these two distributions are basically two delta distributions, right?
Right.
And then the difference is either 1 if they don't pick the same action, or 0 if they pick the same action, right?
Right.
Okay, so now let's generalize it a little bit. So let's see both policies output the distribution over actions. Right? So both of them are distribution over actions. So this is just the L1 distance between two distributions, right?
Oh, I see.
Right? And I can write this as 2 or 1 over, sorry. So I can write this as 2 of the total variation distance between two distributions, right?
Okay, I see. So just to clarify, the pi's return some probability distribution over all the actions, and then you're just subtracting those two vectors and taking the L1 norm, right?
Yeah.
Okay.
And another way to interpret this is think about this as total variation distance between two distributions used by policies.
Okay. Right? That makes sense. Yeah.
Like it's a metric, it's a divergence measure of two distributions. Right. Again, you can interpret this like a way to sort of get an intuition is that think about policy as deterministic, but think about deterministic policy as a distribution where you put probability mass 1 on a particular action, right? Yeah, so here I'm basically saying that you can upper bound the performance difference by the policy disagreement, right? Measured under L1, averaged over one policy's trace, right? So here we're only concerned about one trace, right? One policy's trace. Right, so yeah, so any questions about the performance difference lemma? So yeah, so if this is the first time you see this kind of thing, it's a little bit, yeah, so it's a little bit annoying. So I think a good way for us is to like, read definitely try to read the lecture notes that posted today, which has a detailed derivation for performance difference lemma, right? And the next slide, we will look at an application of performance difference lemma for the policy iteration algorithm. All right, so let's just look at how we actually can use it, right? Let's use it in an algorithm that we understand pretty well now. So policy iteration. All right, so let's go back to the older policy iteration algorithm, right? Where we record that policy iteration updates the policy by acting greedily with respect to the Q function, and we talked about that we can completely rewrite this as a greedy policy with respect to the advantage function of the column policy. Pi t, right? This you should convince yourself is just argmax over A. All right, so a while back we showed that this policy iteration gives us policy monotonic improvement, right? So let's just say if we can use performance difference lemma to prove that monotonic improvement in 2 steps. Okay, so to show policy improvement, we just needed to compute the difference between these 2 policies values, right? So that's the performance difference between these 2 successive policies, pi t plus 1 and pi t. And just apply PDL here, right? So this is what we got. So PDL is the advantage of the older policy averaged over the current policy's state action trace, state action distribution. Right, so this is a bit annoying. Like you care about the performance improvement. So performance difference lemma tells us that the quantity can be quantified as the average advantage with respect to the older policy, averaged over the current new policy state action trace. Right, so everything is equality. There's no inequality yet. Oops. Okay. All right. So because here everything is deterministic, every policy is deterministic, right? Because this is a deterministic rule. So again, think of deterministic policy as a special case of stochastic policy, but you put every probability mass onto one particular action. Right. So here, what I did is just put the expectation inside this advantage, right? Because everything is deterministic. I'm only selecting an action deterministically. All right, and then now I can just use the definition of pi t plus 1, right? Pi t plus 1 is a policy that picks the action that has the largest advantage, right? And then of course, the advantage of this guy, the advantage of this is larger than the advantage of the previous policy pi t, right? Because this by definition is argmax for A pi t SA. Okay, and by definition of an advantage, the advantage of itself is actually 0, right? So this is actually 0. Because you don't get an advantage if you keep following yourself, right? You never deviate, right? The advantage of the action from yourself is actually 0. Okay, so we just proved using 2 steps by calling the performance difference lemma, and then 2 steps we prove the policy improvement lemma, the monotonic improvement lemma for policy iteration. Right? So you can see this is pretty useful because if you care about whether or not your new policy is better, you can just apply performance difference in the first time step, right? And then you can do some reasoning to sort of convince yourself if there's an improvement. This is just a very simple application of PDL for policy iteration. But we will see the application of PDL for some other algorithms in the next few lectures. Okay. Any questions about this very simple 2-step proof? Of course, this step hides a lot of this step. It's a direct application of PDL, but this itself hides tons of derivations, right? But if we are comfortable about the PDL application, then the rest is pretty easy, right? Yeah, and again, the motivation of studying PDL is really this is a useful tool for us to quantify if our algorithm is actually making monotonic improvement, right, between the two successive policies that it computed. Right, and one thing that I want to mention is that this performance, one thing that I want to emphasize again is that the performance difference is actually kind of nice because this quantity is the difference between potentially two completely non-overlapping trajectories, right? So, and these trajectories are infinite length trajectories. It's really hard to reason. But now if you look at the right-hand side, this is just concerning one step difference, right? Because the advantage function is essentially saying that let me just deviate from the current policy for one time step, just one time step, right? And let's see what's the advantage. Sort of this advantage value is sort of a one step local quantity, right? While the difference between two policies, they are potentially the difference between two completely non-overlapping infinite length trajectories, right? So we don't want to reason, these quantities infinite length trajectories, right? So the performance difference lemma allows us to just zoom in into each time step and just look at what happens locally if we deviate for one time step, right? So this allows us to reason the difference between two infinite length quantities to a bunch of local terms, right? And this is exactly something that we can actually control, right? Like in policy iteration, like we only do one step local improvement. And then by using performance difference lemma, we show that this one step local improvement actually leads to monotonic improvement for two policies, pi t plus 1 and pi t, right? Okay, so that's basically the end, almost the end of this lecture. So we have some time. So I just want to quickly recap about the recent 3 lectures. This one, the one on Tuesday, and the one on last Thursday, right? So we're talking about 3 pretty fundamental ingredients for RL and Markov decision process. Right? The first one that we talked about last Thursday is the simulation lemma. So this result concerns the question about the performance difference of a single policy pi under 2 different Markov transition probability, p hat and p. Right? And then today we cover this performance difference lemma. They're kind of similar, but the question that PDL concerns is the performance difference of 2 policies under a single Markov decision process pi. Under a single Markov decision process p. Right, and as you can see, this is quite useful for model-based RL. Right, so if you use data-driven approach to learn a Markov transition, and then you might want to use simulation lemma, right? Because you want to quantify the difference of a policy under your learned model and the ground truth model. Right? And this we will see is very useful for those policy improvement algorithm. Right? Because this is exactly the question that you care about, right? You make some update on your policy and you want to ask yourself, whether or not my new policy's value is actually better than the previous policy's value, right? But you sort of care about these quantities under the same Markov decision process, under the ground truth Markov decision process, right? And the last piece is how we actually draw samples from the state action distribution and how we get an unbiased estimate of our Q value. So this step corresponds to the rolling in process, and this step corresponds to the roll up process. right? So these are the three ingredients, and they often used over and over in many, many algorithms. Right, and then we talked about two algorithms. The first one is pretty straightforward. So that works for the generative model setting in the sense that you can reset to any state action pair, and then you can get an observation of the next state. Right. Generative model says that you can reset and observe S prime over P, say. Right? We're talking about an algorithm where you reset many, many times and get an observation for the next state many, many times and do counting and compute the ratio. And then we convince ourselves that P hat will converge to P if the number of experiments converge to infinite. Right? So if you still recall the confidence ball or confidence interval idea. Right? And then we just do planning in the learner model P hat. So that was the algorithm. And the second algorithm is this approximate policy iteration algorithm, where every iteration, we use a regression oracle to compute an estimation of our policy's Q bet. Regression oracle computes a Q hat T that is aiming to approximate Q pi T. And then we do the usual policy improvement step. And of course, this algorithm has some flaw in the sense that it cannot guarantee monotonic improvement unless your training distribution is very diverse. Right, so that's basically what we covered in the last 3 lectures. Right, starting from next week, we will talk about incremental policy optimization approach. Right, recall the failure cases of approximate policy iteration. Right, we cannot guarantee that the new policy will be close to the current policy. Right, the new policy will be completely different from the new policy in the sense that the state action distribution they visited, the state actions pairs they visited could be completely different. So our previous estimator will be completely invalid, right, under the state action distribution of a new policy. So that will cause significant problem in the sense that we cannot guarantee our policy improvement step is like making monotonic improvement actually. Right, so the next few lectures, we will talk about different ways to force incremental update in the sense that I want to make sure my pi t plus 1 is kind of close to pi t, right? Not too far away. So that we can make very steady, monotonic improvement until we hit some, plateau, for instance, some local optimal solution.